Okay, good morning or good afternoon, maybe in your local time. Hope you have a good rest last night and fresh and excited for today's session. After several days of discussing about astronomical aspects of dark matter, today we will hear about astroparticle dark matter. We have here with us Dr. Reinard Primulando. Dr. Primulando received his BSc in Physics from Institut Teknologi Bandung and got his MSc and PhD in Physics from the College William and Mary in Virginia, USA. The title of his doctoral dissertation was Dark Matter in the Heavens and Colliders, Models and Constraints. He published many papers on phenomenological astroparticle physics, including neutrino and, of course, dark matter particles. He is now the chair of the Department of Physics in Parahyangan University in Bandung, Indonesia. So now, fasten your seatbelt and get inspired by the journey he will lead us to the world of particles. Dr. Primulando, please start.
Okay, thank you very much. Let me share my screen first. Okay, thank you. Thank you for the invitation. It's always nice to, to talk, to give a talk and to discuss about things that I really love and love to do and love to, work on, which is the dark matter and particle physics. Let me tell you, I'm probably the only one odd here. I'm not an astronomer, but I'm more like a particle physicist. My work is mostly on particle physics phenomenology, but dark matter is one of the main interest in the particle physics community. So that's basically part of the things that I work on, besides other things like Higgs or other stuff. Now I'm going to tell you about particle dark matter. Dr. Wulandari told me that I should talk about collider. I will spend a lot of my time into it, but I will also talk about many other aspects of particle dark matter, because I need a lot of good motivations before going to collider. Yesterday you were given some reviews, very good review on dark matter, and now from the observation that we have seen so far, we have good evidence that this the dark matter is particle. I'll just put quotes here, particle, because you'll see that particle in a quite broad sense. But the difference is then usually the modified gravity has a hard time to explain the dark matter in all scales. But you'll listen later to the talks, alternatives to dark matter. But right now, at least most of the hints out there points out to dark matter being particle. I'll explain to you what particle they are later. So there are two. These two has been discussed yesterday in the intro to dark matter. One is the bullet cluster. In the bullet cluster, you see that the distribution of the hot gases, the baryonic matter, and the matter is not the same. So the distribution are not the same. So it's kind of hard to to reconcile this problem with the if you assume modified gravity. But the other quite strong hint, it comes from the structure formation. because we need a cold dark matter to be the seed of the structure, the galactic, the large scale structures. If you had modified gravity, usually there is a radiation pressure between normal matter, so it cannot collapse. The structure cannot collapse soon enough to produce the structure that we seen today. So we have a good hint that the dark matter is actually particle in broad sense, not modified gravity. Now assume that we believe that, so assume that it's true. Then the question is like, well, what particle is it? The answer is we don't know. If I knew the answer already, then we probably will not have this class, because basically they will tell you in the textbook, like in your undergrad days or grad school days. But now it's a mystery. How much mystery is it? We don't know, and a lot of things in the particle dark this particle dark matter. We don't know if we don't know its spin. Really, we don't know. We have no idea what spin it is. 0, 1/2, 1, 3/2, or whatever. We have no idea. We have no idea about its non-gravitational interaction. So the only hint of dark matter that we have so far is from its gravitational interaction. Starting from the rotation curve, even like to large scale structure. We just know that it has to pull some baryonic matters into it. So we know it interacts gravitationally. We have no idea how does it interact between us and the dark matter besides the gravitational interaction. We have no idea if it is fundamental particles, like you might heard electrons, or you might heard about quarks. Those are type of fundamental particles as we know it. So it's like you cannot divide it at all. Or it's composite, like nucleons is a composite particle, or proton is composite of quarks. Nucleus is a composite of nucleons. Or even like this could be like a very large composite dark matter, or could be even like the black hole, primordial black hole to be exact. So we have no idea about this, and even we have no idea what's its mass. Is it as heavy as proton, as heavy as electron, or whatever? We have no idea. Let me focus a little bit about its mass. So to tell you like how much we don't know about dark matter. Let's see. Let's put some bounds on the dark matter mass. So I'll put the so this is the bounds on dark matter mass. DM mass. Let's put the lower bound. What is the lower bound on dark matter mass? The way we imagine of the lower bound is if the hint, the smallest thing that you see the dark matter hint. You don't see the dark matter hints in the, for example, like you don't see dark matter effect right around us, right? We don't see dark matter effect in the solar system scale, but you start to see the dark matter effects, meaning through the iterational curve in the galactic scale. The smallest scale that you think of is the dwarf galaxy. You basically can see a lot of you can see the rotational curve in the galaxies, dwarf galaxies. It doesn't agree with the expectation if you only have the baryonic matter. So that's the scale that you see. You start to see the dark matter hints. So that will also what we see from those hints, we see that at least at that scale, the dark matter behaves classically. What do you mean? So in other words, there is no quantum effect. So you don't see the dark matter behaves like quantum, like, it's moving from one place to the other place suddenly, you see that it behaves like, classical particles, like, the particles that we know, like, like me and you, that we don't see quantum effects happening in our scale. So at least in the galactic scale, we know that or dwarf galaxy scale, we know that the dark matter doesn't behave like quantum particle. That tells us that the de Broglie wavelength, if you remember in modern physics, de Broglie wavelength of the dark matter has to be smaller than the length scale of the say dwarf galaxies, right? The de Broglie wavelength, you might remember, even some high schools actually teaches de Broglie wavelength is h over mv. So I'll because usually people in particle physics will say dark matter is chi, so I'll just put m chi here times v, smaller than L dg, these dwarf galaxies. So we have a lower bound on the dark matter mass to be what is it? You go over here. So h over L dg times v. We know what h is. H is the Planck constant, 6.6 times 10 to the minus 34. The unit is electron second, if I don't remember, same unit with momentum. LDG is the scale of the dwarf galaxy. So it should be around kiloparsec. You can turn it into meters, of course. And V is the velocity of dark matter. So if we assume the dark matter has been virialized, remember the talk yesterday about virialization, we can safely assume that all dark matter these days have been virialized. So you can calculate the velocity of dark matter, but by the assumption, and the average velocity of dark matter is around 10 to the minus 3 of the speed of light. So it's about 300 kilometers per second. You plug it in into, plug these numbers. This is a very small number, 10 to the minus 34. This is a huge number, kiloparsec, and it's quite a huge number. So you'll get a very, very small number. I'll just do the calculation. I have the notes, of course, so I don't have to do the calculation right now. It would be around 2 times 10 to the 58 kilograms. Now, if you're a student of physics or astronomy, you should try to build a sense on, like, the orders of magnitude. 10 to the 58 kilogram, is it big or is it small? It's very, very small. Imagine, so the proton mass is 10 to the 27 kilograms. The electron mass is 10 to the 30 kilogram, about 10 to the 30. So this is much, much smaller than the electron mass, but this lower bound. So the lowest possible bound on the dark matter mass is much smaller than the electron mass. I'll put it in the unit that I like better. Then we'll discuss about this unit later. It should be 10 to the 22 eV over c squared. So this is like, this energy over c squared, because we have EMC squared. So this is a correct unit. Just if you haven't seen the EV, it's a unit of energy. 1 EV is 1.6 times the minus 19 joule. So this is ED over c squared. I like this unit better, and I will tell you about this unit later. It's natural unit, so it's the language of particle physics. So it's 10 to the minus 22. That's the EV per c squared. So this is the number that you have to remember. So that's lower bound. Okay, lower bound on dark matter is very light. What about the upper bound? The upper bound is basically, again, we should look at the hint of dark matter. The scale that we see the hint of dark matter is the galaxy, and you have a nice peaceful spiral galaxy here. Well, peaceful or not depends on what you're looking on, but I'll see, like, this just spinning around and it's nice. You have this here, but imagine if the dark matter is very heavy and you have the heavy dark matter just sitting around here. What happened? if the dark matter is heavy enough, then this disk will get pulled over to the dark matter, right? Because dark matter, if it's really heavy, then it'll put some gravitational pull into this disk. Well, we don't see it. We basically see that the the spiral, the disk here is just moving around and enjoying their life, basically, not getting pulled by the dark matter. So that's one upper bound that you can put. So if dark matter is heavier than some value, then the disk will get pulled over. But actually, there is a slightly stronger bound that you can put in. It's basically from this global cluster. If you remember, global cluster is like compact galaxy cluster, and it's very old. It's quite compact, quite dense. So if the dark matter, it cannot sit here. Otherwise, it has to rotate. I told you it has a velocity even like 1/1000 of the speed of light. So it moves around, and then eventually it will get closer, quite close to this global cluster. What happened if the dark matter gets closer? Then the stars in this global cluster will get pulled, and then the structure, the nice compact structure, will just like it will disappear. So there is no global cluster around. So and global cluster is quite old, so it has a lot of time to interact with dark matter. And yeah, that's how you get the upper bound on the dark matter mass. And what's the upper bound? I don't do the calculation, somebody else did, and then they get the value of the dark matter mass is about 1,000. It has to be less than 1,000 of the mass of the sun. All right, then this is 10 to the 67 EV over c squared. That's the number that we had in the unit that we used before, EV over c squared. So now we know that the dark matter mass is between the 10 to the minus 22 EV over c squared and 10 to the 67 EV squared. That's our only knowledge about the dark matter mass is. We have the lower bound and we have the upper bound. What is it? We have no idea yet. I hope we have some ideas in the future, but right now that's the only idea that we have. This is you can just do subtraction. This is 89 orders of magnitude, right? This 89 of magnitude. This is huge, orders of magnitude to search for dark matter. So you think it's just a number, yeah, 89, 90, 50 orders of magnitude. Like it's just a number. No, it's crazy if you think about it. So let me tell you a little bit about orders of magnitude. The size of a proton, or nucleus, the size of proton is 10 to the 15, 1 femtometer, so 10 to the minus 15 meter. Okay, the size of this is proton. The size of a known universe is, I even have to try to remember myself, is 10 to the 27 meter. Okay, this 15 is, so there is a, how much, like how many orders of magnitude difference here? So there is 42 orders of magnitude. Even the size from of the proton to the size of known universe is only 42 orders of magnitude, and we know everything inside it, kinda. But this is dark matter mass. It's 89 orders of magnitude. So it's, imagine like you're looking for kind of proton inside the universe. This is like you're not even looking for needle in haystack. It's like you're looking for dark matter. It's like you're looking for not proton in haystack. No, it's even bigger. It's a proton inside the universe. No, it's proton inside the universe. Only 42 orders of magnitude. It's 89 orders of magnitude. So it's crazy. It's like our what we don't know about dark matter is crazy. That makes our life a little bit harder because that means that the physics here and the physics here at the 10 minus 22 and then 10 to the 67 would be different. And then we don't know how to, if you are given this number, then we have no idea how to look for dark matter, honestly. But then, so we need a little bit guidance from, some theories. That's what I'm going to tell you today. We need some guidance on how to look. So we need some, hints from the theories, and the theory will tell the experimentalists on how to look for dark matter. So this is a brief review on the theories out there. The most famous one is this GeV200 TV. I think Dr. Wulandari has told you yesterday. So it's basically went onto this this chart, albeit different way to say it. So this is WIMP. So lighter, we call it light dark matter. It consists of some dark detectors, thermal neutrinos that can be thermal or can be not. So lower than 1 keV, we call it like something like ultralight dark matter. It has to be bosonic, and then it could be QD axion or something else. It doesn't have to be QD axion. Could be axion-like particles. Going to heavier, heavier mass. It could be some composite dark matter, something called Q balls, nuggets, and all those stuff. But if you believe in particle physics, or quantum field theory works up to up to gravitational scale, then you have a you have a wall where the particle cannot be fundamental anymore, which is the Planck mass. Planck mass is about 1 nanokilogram, so it's kind of small, but as a fundamental particle, it's quite large. Beyond that, you cannot have fundamental particles anymore, so you have a composite or just primordial black hole. So what I'm going to talk today, but you can ask me about other stuff if I know the answer, because the landscape is very fast. I probably don't know all the answers to questions around these models, but I know some. So you can ask me questions about this later. But what I'll focus today is the WIMP, because this is the main guidance for the experimentalists or to astronomers to look for the WIMP, to look for the dark matter. Because it fits quite nicely. This picture fits quite nicely into the picture of dark matter and particle physics. This one I'm going to talk today. But before jumping into WIMP, we have to go through some laundry list of preliminaries. Okay. Preliminary number 1. I will have to tell you about natural unit, the one that I kind of hint to you sometimes ago. Natural unit. In the natural units, probably some of you have seen this natural unit. It's you said h bar equal to 1, c equal to 1, and kb, the Boltzmann constant, equal to 1. Some people even use g equal to 1. I don't use it here, but particle physicists tend to not set g equal to 1, but they tend to set this h bar, c, and kb equal to 1. It's kind of natural. It's really nice. Natural unit is actually really nice when you do back to the envelope calculation. That's the thing that we are going to do today. Actually, back to the envelope calculations. So to get you some ideas about natural unit. So when you set this is unitless. This one, the unit of temperature, for example. So remember, you have some equation like E equal to kb times T, 3/2, usually put 3/2. 3/2 is unitless, kb is unitless now. So you have the unit of E and T to be the same. So in this natural unit, T has the unit of energy. What about the mass? The mass is E mc squared, right? So C is equal to 1, so E has the unit of energy. M is the unit of energy as well. not E. E, of course, has the unit of energy, but M has the unit of energy. The length, meter, in meter is in standard unit, but now it has a unit of 1/energy, and the time has a unit of 1/energy. You can easily switch back and forth. You can actually do some calculation on that, but usually I just look at some tables just to make my life easier. For example, temperature 1 GeV of temperature is equal to what is it? 1 GeV of temperature is equal to 1.2 times 10 to the 7 Kelvin. For example, you can switch this and back and forth. The mass is easy because EMC squared. So 1 GeV of mass actually is 1.78 times 10 to the minus 27 kilograms. This is quite nice actually because 1 GeV is 1 giga electron volt. So remember again, 1 EV is 1.6 times 10 to the minus 19 joule. Therefore, 1 GeV, if you want to convert energy to EV to in the SI, GeV to EV is just 10 to the minus 10 joule. In natural unit though, 1 GeV of mass is 1.78 10 to the minus 27 kilogram. This is nice because the mass of proton and mass of neutron is approximately 1 GeV. So it's easy to remember. What about the length? Well, let me go to the time first because, just 1/GeV, or let me just put it here. Put it this way. 1 GeV to the minus 1, so 1/GeV. In unit of time is 6.6 10 to the minus 25 second. And for the length, 1/GeV is 1.97 times 10 to the minus 16 meters. Let me for the length, let me discuss this a little bit. So 1/EV, not GeV, 1/EV in the unit of this natural unit, if you translate it into the length, would be 1.97 times 10 to the minus 7 meter. And this would be 0.7997. And this would be 0.197 microns, right? So this is interesting. Why? Because in this natural unit, 1 EV is equal to this. Remember, so you get a sense of what microwave is. So microwave is, you want to heat the water using, electromagnetic wave, and you want to know what the wavelength is. In this natural unit, it's super easy because the energy level of water is about 1 EV, right? The energy level of the hydrogen is the ground state is 13.6 EV, but for water, it's because it's molecule, the energy level is about 1 EV-ish, slightly less than 1 EV, but about 1 EV. But that tells directly to you that the wavelength that you require, you need to heat up the water is, if you convert it into, is 1 EV actually. In the natural unit, it's 1 EV. If you get confused, okay, what is 1 EV? Just convert it back to the standard unit, SI, then you get the wavelength that you need is about this order of magnitude gas, so it's about microns or microwaves. So it's, you don't have to think about too much physics. Everything here is back envelope calculation, and you get kind of correct answer by going to this natural unit. So this is very powerful. Actually, if you have seen this, you should appreciate this. If you have not seen this, well, if you jump into something like particle physics, then you should get used to it, and you'll actually have fun. using this this thing and this mathematical calculation. So the second preliminary that I want to tell you is the cross section, because this also will be very important for us later. So we have the cross section is basically it tells you like how much. So you have, if you have two stuff here, one is say A, the other B, and you want to collide them, and so in these two stuff has a lot of constituents in it. Like say if you have two beams and each beam has proton inside it, you know, then you collide them. Now the question is like some of this particle will just pass through each other and they will not interact, but some of them will actually collide, and then this, for example, this and this will hit each other and they will collide. Some will just pass and then don't do anything. So the cross section is the one that tells you like how many of these will interact. The cross section is given by the number of events, so the number of interaction, how many that interacts, how many of these interaction happen, is this definition cross section. So here, just don't argue with a definition, is sigma is cross section times this is not a good name, A and B, because I'm gonna use A and B again, just 1 and 2 then. Sorry, 1 and 2 and 1. So number of particles in the in this cylinder, doesn't have to be cylinder though, in this one clump of particle, the second clump of particles divided by A is the area of this. So this is the area, this area, this cross section, the area of the beam basically. So that's the definition of cross section. So then so we can work it out. So sigma, which is cross section, is 1 and 2 multiplied by A. So the unit of cross section is actually meter squared, right? The unit of the area. Usually people don't use meter squared. Sometimes people see meter squared, but you'll see, especially if you look at the direct detection plot, sometimes they put it in meter squared or centimeter squared, but sometimes they put it in barn. That's another unit of cross section. So 1 barn is 10 to the minus 28 meters squared. Okay. Usually, if you look at the direct detection plots, it'll tell you in picobarn. So just just put it in minus 40 meters squared. That's it. Yeah, and so this is meter squared. In natural unit, it would be what? It would be meter squared, but then in natural unit, since meter is 1 GeV, so this is 1 of energy. So sometimes I'll put it in 1 GeV squared. Okay, that's the cross section. So let's do the conversion. 1 GeV to the minus 2. What is it in terms of barn? It would be 0.358 millibarn. So if you put it into barn, it would be just 3 times 89 10 to the minus 4 barn. If you change it into meter, it would be 3.89 times 10 to the minus 32 meters squared. It's actually kind of interesting because it's 10 to the minus 32 squared. So imagine this unit of area, right? What is the radius of a circle that has this radius of the circle that has this area? Well, just take the square of it, right? So it's the radius of this circle that has this area would be around 10 to the minus 16 meter. 10 to the minus 16 meter is kind of the radius of proton. Remember, the mass of the proton is 1 GeV. So the cross section, quote unquote, of proton is 1 over GeV squared, and then well, the radius of proton is 10 to the minus 16 meter. So it's kind of, everything is kind of fall in together. So preliminary number 3. We have 4 preliminaries, but this one is quick. Number 3, I think you have seen this, is about the critical density of the universe. I think you have heard this before. Critical density is the density required to have a flat universe, and we are in kind of, you know, as far as we know, we live in the flat universe, not flat Earth, flat universe. So this density that's required to have a flat universe, and then you can actually work it out. I'll just put the number. The critical density is 8.53 times 10 to the minus 30 gram per centimeter cube. This is equal to, if you put it in the kilogram per meter cube, it's just few protons inside a meter cube volume. We want to put it in the natural units, so this 3.66 times the minus 47 GeV to the 4. Yeah, GeV to the 4. You'll use this number once actually, so you don't have to really remember this, but I'll remind you later. But the dark matter density, defined as yesterday, Dr. Reinard told you about omega. So omega chi, or omega dark matter, is the ratio of rho dark matter divided by critical density, is 0.265. Yeah, it's about, you know, 20 something percent of you know, total budget of the universe. So this is the number that you probably should remember. 0.2, you know, 20% of the critical density. And this is the longest preliminary before we dive into the meat of the talk. Is statistical physics. This is just a review, just in case you don't, or you want to sleep during your statistical physics class, you thought it wasn't important. You know, the fun is in the, you know, stars, galaxy, cosmology, but really, if you do cosmology, you have to know about physics and statistical physics. It's a reminder, just because we need that later. I hope you have seen this. The number of particles in statistical physics is, you know, is just, yeah. Let me just write down the equation. Is the integral of, you know, the degeneracy that you have multiplied by the weight. This weight is, you know, depend on the fermion or bosons, and multiplied by the volume. The volume in the spatial and the spatial and the momentum, because this weight is a function of position and momentum in general. So multiply by divided by 2 phi h bar to the cube. Why we have this? Because we have you know, the smallest volume element that you can take depends on the uncertainty principle, Heisenberg uncertainty principle. So it tells you that you know, this. Yeah, this tells you that about the uncertainty principle. Now the Fs, I'm not sure if they write it this way or the other way in your class, statistical physics class, but I believe that this Fs is written in very standard form in your class. It would be 1 over E to the E over mu over kBt, but we take kb equal to 1, kBt plus minus 1, where plus is Fermi-Dirac distribution, and minus is for Bose-Einstein. So really, this one you should have seen if you not fall asleep during your class or just miss the class. This one is might not be that standard. I don't know how your professor wrote that in the blackboard, but this one is very standard. So E, this is the one that depends on X and P is the E. And usually for our interest, usually it only depends on the momentum. Now from this we can, if it only depends on the momentum, not the position, so we can take this d3x out of the integration. So because it becomes just become the volume, and we get the n, which is just the number density, n over v equal to gs a constant. It doesn't depend on momentum, of course, the degeneracy divided by this constant. So I'll just pull it out, 2 phi to the cube integral of so we're only left with this fs xp d3p. We will also need the energy density, which is rho. Just have this weight multiplied by the energy, of course. E as a function of P, d3p. So what is it? Yeah. So let's do a simple example calculation here. Well, before we do a simple calculation, what is the E? E is just usual. We work on, we could have relativistic particle and non-relativistic particle, but E for the relativistic particle is given in special relativity. E is equal just p squared plus m squared. Wait, well, yeah, it looks different because I take c equal to 1 here and here. So p here is equal to e squared minus m squared. Now, if you differentiate this, it would be 2p dp equal to 2e dE. Very good. Therefore, this d3p here, we can work out this d3p here is equal, it's just equal to this volume. So assume that it's kind of isotropic, mostly isotropic anyway. So well, yeah, the F is isotropic, right? It's the same on direction because the E is isotropic. It doesn't tell you what direction it is. So it's d3p is just 4 pi, right? 4 pi p squared dp. But we know that p dp is equal to EDE. So if you want to express in EDE, the p is e squared minus m squared and EDE. Oh, sorry, my bad, EDE. Very good. Now let's do one example. I want to calculate the rho of photons. Photons, we know it has the mass equal to 0, and you can easily create and destroy photons. So the mu is equal to 0. So what do we have? We have here this is the equation, right? Photon is Bose-Einstein particle, so you put minus here. So rho it's equal to gs for photon. It has to be 2. Let's just put it 2, right? I can put it 2 here. Gs photon has only two polarization, right? Either left, right, or or clockwise, anti-clockwise. 2 phi cube, right? You have 2 phi cube here, and sorry, this is gs 2 phi cube, and you integrate over fs. The fs is this. So integrate from 0 to infinity. Fs is e to the energy. mu 0, so e to the energy over t minus 1. And then just plug it in here, right? The 3p, oh sorry, there's an e here. So I'll put e here because we want to calculate a rho. E here, and then the 3p is just this. So 4 pi e squared, right? E squared t. You know, this is 4 pi here. There is 4, 8. So you have many things flying around here, and then you get 1 over 5 squared, e to the cube over e over t minus 1 d. So let's assume something to make this integration slightly easier. Let's assume x equal to e over t. That means that e is equal to x times t. So this row integration, is equal to you have t, but t is not a function of x or e anymore, right? So t you can pull it out of the integration. So you have t to the cube here and t to the 4th. So t to the 4th divided by 5 squared integral of 0 to infinity x cubed over e to the x minus 1 dx, right? This integration you can either, you can go to Maple, Mathematica, or just Eclipse, and it's in the back of every statistical physics book. Basically, it tells you that it tells you what the integration is, and then if you do it, you'll get the answer of this would be 5 squared over 15 t to the 4. Okay, this is the answer that we need. Remember, this is just usual Stefan Boltzmann rule, right? Stefan Boltzmann, the sigma is, usually you have the power is sigma t to the 4th, right? The sigma is just this, actually. Well, in some unit, we use SI unit here, but really, I'm just redriving Stefan Boltzmann law, and this actually you do it a lot of, all of statistical physics class does this calculation. So yeah, I just redriving this Stefan Boltzmann law here, but yeah. But now we will need, I will not do it here, but we'll need the n for non-relativistic particle. So the calculation is the same. Of course, this thing is different. So the integration is slightly different. You have E here, but you don't have E here, so it's slightly easier. But for non-relativistic particle, I will need that to do the WIMP, and I'll just pull out the answer. It's GS m t over 2 pi 3/2 e to the minus m minus mu over t. We'll also need this result later. So we need this and we need this. So bear in mind, you don't have to remember everything. Of course, this is a little bit too much, but you have to remember that n is proportional to 3 to the 4th, and there is an e here. Also, rho in the case of the rho is t to the 4th for relativistic particle, basically for radiation. Okay, very good. So how do we do this? How do we do this? Let's dive into WIMP, WIMP paradigm a little bit, and then Dr. Wanderi, how do we do this? I forget to ask you. Should we set aside like last 20 minutes for question and answer, at least in this session? Or I think that would be I hope that will be a better idea. So I'll just go into WIM and I'll stop at WIM. Then later I will go and talk about the how to detect WIMs. So this is the WIMP paradigm. So we are done with the preliminary, and then we jump into the WIMP paradigm. Yesterday, it was told, you were told that WIMP is a kind of nice paradigm. It's weakly interacting magnetic particle, and now we're gonna go a little bit deeper into that. Yeah. So this is an example of WIMP freeze out. So yesterday it was told, you were introduced to something called freeze out. So let me just go a little bit deeper on what WIMP freeze out is. So back in the universe, the temperature of universe is much higher. Also, it was more dense. So then, back in the day, you can easily create dark matter particle by basically have two standard particles. Standard particles meaning that quarks, leptons, or photons, or anything that smash to each other and create a dark matter particle. Also, the other way around, the dark matter particle could annihilate and then disappear and become standard particle. So these two processes going back and forth. That means that the standard model and the WIMP, or the dark matter, they are in equilibrium. Now, at some point though, since the temperature goes lower and the universe expands, it's getting harder for the standard model to find the other pair. Standard model doesn't decay into the dark matter, of course, because we still here. But the standard model particle has to find another standard model particle to create WIMPs. So that's what happens as the universe gets larger. At some point, the standard model particle simply cannot find the other standard model particle anymore, and that's it. Like the number of WIMPs just stays around. That's what's called freeze out, because you have created enough WIMPs, some WIMPs, some dark matter. Before the process going back and forth, you create and destroy WIMP, and then at some point you just cannot create anymore, and also the WIMP cannot destroy to each other, because it's universe expand also for the WIMPs, right, for the dark matter. So it cannot be created and destroyed anymore. So that the number freezes out. That's what we need. So it happens. I'll do the back to the calculation. It happens when the rate of this interaction is proportional, is approximately equal to h. So what's the rate of this interaction? Rate of interaction, the h is the Hubble parameter, Hubble constant. This rate is, I will say that it's equal to the n number of WIMP times sigma times v, the velocity of the WIMP at the time. Is the unit correct? Well, let's check. N is just 1/meter cubed. Let's do it as I, because you are more familiar with it. Sigma is meter squared, and the v is meter over second, right? Meter over second. So what you'll see is it's m cubed divided m cubed 1/second. The unit's correct. It's a rate. What we'll take, since we are going to do back the info calculation, this v is equal to 1. Okay. Later we'll see it's not equal to 1, but for the back of calculation, it's fine to say it's equal to 1. So that's rate. So we want to know what sigma is. N is just this n, basically this n, because they are in equilibrium. And back in the day, we freeze out in the most model, the WIMP is non-relativistic. That's why I told you we need this n. And then sigma, it depends on the theory, and p, you take it equal to 1. Yeah, very good. Now, what is h? Well, h is the Hubble constant, and back in the day, so let me remind you about the Friedmann equation again. The Friedmann equation, h is 8 phi g divided by 3 rho. I believe all of you know by now this Friedmann equation. And rho, back in the day, the universe was radiation dominated. So that's why if it's radiation dominated, then the rho is given by, you know, this value, pi squared over 15 to the 4. So we just plug it in because it's radiation dominated by t to the 4. Oh, sorry, pi squared over 15. Now, usually we want to put everything in the same unit. So I need to introduce you. I already told you a little bit about the Planck mass, but let me introduce you to the Planck mass. The Planck mass is defined, it's just definition, h bar over c 8 phi g. If you work this out in the standard unit, you get the kilogram as the unit. In our case, we need, you know, we have one, since we set h bar and c equal to 1. So how heavy is the Planck mass? The Planck mass is about, in SI, 4.3 times the minus 9 kilogram. It's quite light, but that's the, you know, that's, but yeah. I'll stop my comment there. But then it's in GeV, it's equal to 2.4 times 10 to the minus 18 GeV. This is the unit that we need. So if 8 phi here, we have G here. Very good. We have, sorry, it is h squared. Somebody should point out this h squared. So we have 8 phi here, so this will become the Planck mass, right? So in this case, our h squared, Hubble h squared, would become phi squared over 45 t to the 4th divided by Planck mass squared, right? This is g. So since Planck mass is 1 squared of g, so it is m Planck, the Planck mass squared. So h is equal to phi over, you know, square root of 3 phi, square root of 3 t squared divided by m Planck. Very good. So this is our setup. Now we want this to be equal to this, right? When freeze out happens. Okay. We can work it out. And sigma, so the rate is proportional to the Hubble parameter, and sigma again was n. So this, I'll put it during freeze out. Sigma proportional to, let's do the back to the envelope calculation. So forget about this 5, since we are not that precise anyway. So T during freeze out squared divided by Planck mass. Good. What is n again? N is it has to be in equilibrium. So it's mt 3 half, and then this take nu equal to 0. So we are left. Forget about GS again. We do back to the envelope calculation. So we have m t m chi. Just put the mass of dark matter 3 half e to the minus m chi t freeze out multiplied by sigma t freeze out over mp. Good. Let's define x usual, because x, we hate everything inside here. So we just put everything inside here, m chi mass of dark matter TFO, and then basically what you will get, TFO is equal to m chi x, right? So basically you have m chi to the, so you have t freeze out here, right? So you have m chi, so you have m chi squared here, so m chi to the cube, and you can put it here. But here you have TFO squared, so you have basically you have m chi squared here, so you would have m chi 1 over m chi here, here just x, and TFO is x squared here, s cubed here. So basically in the end you have something like this: x e to the minus x equal to 1 over sigma m chi m prime. Very good. So now, yeah. So now what's next? Well, what's next? We just need to solve this equation. Well, yeah, how to solve this equation? We have to do it numerically, unfortunately. M chi depends on the mass of dark matter, whatever the number is. Sigma, what is sigma? Sigma, I forgot to tell you the what sigma is. Sigma, again, like is cross section. And the unit is 1 GeV squared, meter squared, so 1 GeV squared. So in most theories, sigma is proportional to G to the fourth. For low enough energy is M chi squared over M the mediator to the fourth. So usually, if you know a little bit for particle physics, so we need some mediator between the chi and the standard model particle, and then this is the mediator, as usually say Z. For simplification, let's set it doesn't have to be just M chi mass is kind of close to mz mass, so it would be G to the 4 M, the mass M chi squared. This is what we use for this at least for this Beckett inflow calculation. Very good. What's G? I'll put G equal to 0.1. Why? Because in QED or in electromagnetic theory, G in this unit usually 0.3. So since we want to do Beckett calculation, I just put G 0.1. And I put M chi. Yesterday it was kind of mentioned that for WIMP dark matter, M chi is around 100 GeV. Say 100 GeV. Very good. So we have sigma. Just plug it in here. We get 10 to the minus 8 GeV, 10 minus 2. Okay. So just plug it into this. So we have 1 sigma is 10 to the minus 8, M chi is 100 GeV, M playing is whatever number that we have, 10 to the minus 8 minus 18. So we want to solve x e to the minus x to be 4.1 4 times 10 to the minus 13. So this one what we want to solve. We have to solve it numerically. So this is what I get if I want to solve it numerically. So this is x e to the minus x, and this is the number of this number of what is it? Number 4. Just look at this: 4 times 10 to the minus 13. So this happens when x is around 30. Okay. The other numbers, let me tell you the other numbers are. The other numbers is, this is for G equal to 0.1 and M chi is about 100 TeV. So about 3 orders of magnitude larger. For the if it is 3 orders of magnitude lower than M chi, this is not here even like it's much lower. It's about 10 keV. So basically, for a broad value of M chi, you get around 20 to 50. But for our particular case, we get M chi equal to 30. So good. You have a square root of x e to the minus x equal to 30. And then what we need is the omega again. Omega, remember, is rho dark matter divided by rho critical density of the universe. And this rho, this is the energy density, right? But energy is equal to mass, so it would be n chi times n chi, right? So this would be rho. But this is the density of dark matter now. So let me just put it in n chi now. So I'll put 0 here. I put 0 here, and then by root C, And then, well, let me just do a little trick here. So I have m chi t freeze out to the cube divided by rho c, and then n0 t freeze out to the cube. Now, we know that the n, the number of density, since it's 1 over volume, right, volume cube, so n is proportional to the the scale of the, not a, but 1 over a cube, right? While the t is proportional to also 1 to the a. So as the universe gets bigger, that the temperature gets lower. So basically, this is this is not freeze out. I bet this is T now. T right now, the CMB temperature, the unit. So then we know that this n over T has to be constant. Very good. Okay, so n over T has to be constant. So this value, n over T, back in now and back in the day, they should be the same. So sigma now, m chi T0 to the cube over rho c, and n freeze out divided by T freeze out, they should be constant. But n, not yet. Sorry, I have to do a little bit trick here. I'll just put m chi because I need the cube divided by rho c, but I'll just divide this into freeze out here, and freeze out divided by T freeze out squared. Now it's squared. Then I can use that equation. So omega chi is equal to this m chi over freeze out is just x, which is 30. T0, we know what it is. Now it's just about 3 Kelvin. Rho c, we know what it is. NFO divided by TFO squared, it's just this value, right? This value. So from this value, we have NFO divided by TFO squared is 1 over mass m Planck sigma. Very good. So we have this nice equation that you can just plug in. Very good. So just plug this value, and then you'll get, TFO is just the, T0 is just the temperature of CMB. Rho c is the critical density. And Planck is, we have the number, and sigma is 10 to the minus 8 GeV. And you'll get this value. Sigma chi is equal to, at least with this 2 times 10 to the minus 50, not 50, 10. GeV to the minus 2 x divided by sigma. Okay, so then if you work that out a little bit, you can work it out a little bit, and then you get sigma chi divided by 0.25. That's the value that we have today. It should be x freeze out divided by 30 multiplied by 2.4 times 10 to the minus 8 GeV squared divided by sigma, right? 2.4 times 10 to the minus 8 GeV. Remember, if this tells you, right, because g to the 4th divided by m chi, right, m chi squared. G to the 4th divided by m chi squared. If g is equal to 0.1 and m chi is equal to 100, then so if g equal to 0.1 and m chi equal to 100 GeV, and you get sigma to be 10 to the minus 8, right? So it's really close to this number. And it tells you, g minus 8 GeV minus squared. It tells you that naturally, if you have the dark matter mass and everything else kind of in the scale of 100 GeV, you'll get a correct density using this freeze out. and that's kind of called that's called Wim miracle, right? It's the number is like 100 GeV. So if you plug in like a very big number, you will not get the correct number. If you use the around 100 GeV or even 10 GeV, this is back to the level calculation, of course. 100 GeV, 10 GeV, or 1,000 GeV or 1 TeV, you'll get kind of correct like density, which is kind of amazing. Why? It's called Wim miracle. If you happen to have dark matter at the weak scale, and the coupling is 0.1, so it's kind of weak scale coupling as well. You suddenly you get a correct like density, and it makes people excited at the time because 100 GeV, that scale. If you remember the mass, what is the mass of W boson? If you remember, the mass of W boson is 80 GeV. The mass of the Z is 91 GeV. And the mass of the Higgs, if you remember the newly, well, it's almost 10 years by now, is 125 GeV. So all these particles live in the weak scale. And there was a problem with this in particle physics because the problem was this mass of the Higgs. So we have this 125 GeV. If you run, if you do the full quantum mechanics calculation, you don't expect this to be this low. So we need something new in this scale, and something new was proposed to be supersymmetry, and the supersymmetry has to have that mass around 100 GeV. Supersymmetry. In supersymmetry, it's natural for you to have dark matter, and the dark matter in supersymmetry happens to be 100 GeV. So it's kind of amazing. Like we have this model that tries to explain the problem with the Higgs mass. And actually, there is a problem also with W and Z mass. And suddenly it has dark matter, and dark matter has correct density by freeze-out. Wow, we have one model that solves everything. It's so that's why people was really excited about this Wim paradigm for a very long time, for decades basically, and they tried to look for this Wim using various ways. So I'll stop here. After that, I'll go a little bit detail into the into this, not too much detail into this freeze out, and then I'll tell you about what to look for the WIMs and other stuff. Other stuff. WIMP and other possible dark matters. Hopefully, we have time. Look for dark matter in this way. But as Dr. Wulandari told me that I have to do colliders, so I'll also spend a chunk of my time in talking about colliders later in the second session. Okay, so I'll stop here. Probably somebody want to ask questions.
Okay, thank you very much, Dr. Primulando. We have 3 questions here. The first question is from Rafi Adnan. Do you want to ask the question by yourself?
Yes, can you hear me?
Yes.
Can you tell us more about the research conducted to reach the upper bound of the mass domain? You said it to be at the scale of 10 to the power 67. Okay.
Okay, I cannot hear you really well, but you want me to tell about this, how you get this upper bound, right? Yes, this is not really my expertise, to be honest. So that's the most story that I can tell you. The most stories that I can tell you is this this assumption that if there is a global cluster is still there intact, and if you have a lot of dark matter passes around, then the tidal gravitational, the tidal force from the dark matter would pull out this this global cluster. I can point out to you the paper later. Maybe I'll just put it in my slide because I still have the second session. But yeah, I can point out you to the paper but I cannot say more than the the tidal wave of the dark matter would just destroy the global cluster. I mean, unless you want to ask for more specific,
No,
like
no,
you can basically you can do some
paper is good.
calculation, right, on the tidal
Thank you.
force on the clusters.
Okay, there's a question concerning dark matter at Atlas, so I will postpone this to the next session. Okay.
Yes.
Okay. The next one is from Muhammad Ridauddin bin Mat Sabri, please.
Okay, can you hear me?
Yeah, I can hear you.
Okay, I want to ask about why the Wim annihilation process must be in equilibrium in that equation that you said before.
That's the assumption.
The assumption.
That's assumption. There are many non-equilibrium production of dark matter, and it will point out to other masses. So, for example, if you create dark matter from non-equilibrium processes, usually you'll get the ultralight dark matter. There are other dark matter productions. So, for example, in fission, usually during reheating, you might get some overdensity of some area that becomes overdense, and that could create some black holes. So from inflation, some of the inflation model points out the presence of primordial black holes. So this if you assume, so we don't know anything about dark matter. That's the problem. So we have to make an assumption, and then we question, like, if we set this assumption, where do we go? So if you assume that the dark matter and the standard model, particle, the particle that we know, were in equilibrium in the early universe, then it will point out that the dark matter mass has to be around 100 GeV. Then theorists or we as physicists or astronomers should question the assumption, right? Okay, let's do another assumption. Let's do that the dark matter doesn't happen, back in the production, it was not in equilibrium. Then you get that the mass of dark matter has to be quite light. And then from that assumption, then you go and search for the dark matter. And different assumption will lead to different ways to detect dark matter. It's basically the whole course itself. You want to go from, equilibrium, which is WIMP, non-equilibrium, and non-thermal, and then how to look for non-thermal dark matter, like ultra dark matter. Those are different stuff. WIMP, direct detection collider, primordial black holes, gravitational lensing, and a lot of things. Gravitational wave also can be used to look for the primordial black holes. So different assumption, different ways. Basically, what we are trying to do right now is to kill all the possibilities, right? If you say, oh, the possibility is crossed, then you go for another possibility. And remember, there are 89 orders of magnitude that you have to cross out. Tough luck. Okay, I hope that answers the question.
Okay, thank you.
Okay, now I will call Emir Shahreza Fadila.
Can you hear me?
Yeah.
Okay. Firstly, I'm sorry if you already mentioned this. Maybe I'm not listening enough. But can you show me the part when you calculate the cross section of the interaction?
Yeah, I think this is the part, right?
Yeah. I want to know why the mass of WIM is approximately equal to the this mz.
Yeah.
I mean the force carrier. Yeah.
Right. So that's an assumption again. Usually, so the reason I take this assumption because it's easier to calculate. Like after this, I will just go very briefly on what to do if you want to break this assumption. But the calculation becomes much harder, and I'll tell you later that you basically don't want to calculate this. It's a lot of pain. especially in a lecture like this. But in reality, we have to, first of all, we don't take them to be the same. It's quite likely they are not the same. But why this assumption is good, at least for the back to the envelope calculation, simple calculation, because in most models, their masses are close to equal. Close meaning that, one is say 100 GeV and the other is 1 TeV or even 100 TeV. They are not that different in most model of particle physics. What if they are so different? It's okay. You can make your own assumption, and then you can think if there is a new way to look for dark matter that way. It's really if you want to discuss dark matter, because we have this this broad of mass landscape. I'm just telling you about the mass, right? I'm not telling you about interaction. The interaction landscape is also this big, and the mass landscape is big. You have to make assumption to look for dark matter. If you have assumption, you look for dark matter with assumption, and it doesn't work, you don't see anything, you move to another assumption. Basically, you just cross up the list like one by one. Yeah, that's the paradigm, because we again because this this landscape is too big, so you have to work one assumption to another assumption. But yeah, but use this assumption that they are exactly equal is too strong actually. So most in a research paper, people break this assumption and they calculate the cross section, not approximately, but really, really really they get real value of this. But usually they don't consider these masses to be too far, way too far. They are close, same order, or one or two orders magnitude larger. That's it. Okay.
Thank you for the answers.
Okay, we have another question, but I don't know who asked this because only question mark here. So I will read this. Can you explain to us with calculation why dark matter mass energy density about 2.241 times 10 to the minus 27 kilogram of per meter cubic?
Oh yeah. Yeah, I don't know where to start honestly, because this question could start. If you want to talk about the experimentalist, then it's not calculation, right? You just look out there and look the CMB or the structure or the galactic rotation curve, and all of them points out to this value. That's the observation. For the theory side, well, this is the example of calculation, right? You assume some equilibrium, and then you work it out, and you have to take assumption on the mass of the dark matter, and suddenly you end up with a very nice. Oh, where did I go? I put too many blanks here. And you point out that with the correct mass, you get approximately, yeah, it's omega over 0.5 equal to 1 is basically this value that you told me, like 2.24 times 10 to the minus 27. So yeah, we can go. Yeah, the question is good, but I don't know how to answer, because I don't know which direction you can go. Either from observation or from the theory. I'm showing you the theory, but from the observation is you just have to trust the people who did that. Okay, thank you.
Okay, next from Rafif Rabani.
Yeah, okay. Hello. In the beginning of the lecture, you mentioned some properties of particles, for example, like spin. So I'm just wondering if we have any constraints for those properties, those characteristics of dark matter particles besides the mass.
Yeah, very good question. The charge is the most obvious one, because we don't see the dark matter attracts the ordinary matter. So usually we know that the charge of dark matter is very, very low, millicoulomb or even microcoulombs. especially it will have some effects on the CMB if the dark matter has a charge, has a charge in the beginning. So yeah, we can get a strong constraint on the charge. On the other interaction besides charge, like whatever the non-gravitational interaction, we would know this when we discuss about dark matter interaction in dark matter detection, direct and indirect detection. The spin, we just have zero idea. You have to detect dark matter first before you know the spin. Really, I mean, the reason is why spin, we have no idea. Spin is a quantum properties, right? When you talk about spin, remember the first time you talk about spin is not when you learn about when you learn about Newtonian gravity or Newton's law. You don't talk about spin. You talk about spin when you talk about quantum physics, right? First time you see the spin of electron, one half, and everything. So spin is a quantum property. As I told you, we only see, as I told you, like dark matter behaves like classical particle. You don't see any quantum effect on dark matter. So you have no idea about the spin of dark matter right now, currently. Once you see the quantum effect of dark matter, for example, from the direct detection that I'll mention later, then you might have some idea about the spin of dark matter. But until then, we have no idea about the spin.
Okay, thank you. Maybe we can take one more question from the audience. Anyone? If not, then we stop the session here. Let's thank Dr. Primulando for now, and we will meet in 30 minutes. Okay, thank you.
Okay, thank you very much.
Thank you. Okay, everyone, we will take a picture before the lecture is end. Please turn on your video. Okay, I will wait. Okay, it will be 2 slides. Okay, please smile. 1, 2, 3. Okay. Once more. 1, 2, 3. Okay, thank you. Bye-bye.
Okay, see you in the next session.
Thank you.